Hello everybody and welcome back to Controlling PID playlist. In this video we will talk about the PID control. We will first implement the classic PID controller and later we will also add the Antiwind app scheme. Our goal remains the same, hence we are aiming at controlling the ball position and satisfying some performance requirements. In the previous video, we have seen that the PD and the PV controller weren't able to eliminate the steady-state error caused by the external disturbance. So now we are moving one step further, introducing the integral action. In fact, as anticipated by this table, we will see that the integral action manages to eliminate the steady-state error. This is the transfer function of the PID controller. Compared to other controllers we have seen, the PID controller adds 2 zeros and it also adds 1 pole. Moreover, as mentioned before, it eliminates the steady-state error. Since there is a derivative action, we still need to use a low-pass filter to reduce derivative kick. Let's insert it into our block diagram. And let's compute the closed-loop transfer function. This time it is a fourth-order transfer function. The characteristic polynomial is a fourth-order polynomial. Also in this case, to design our controller, we will leverage polynomial factorization. But this time, the residual polynomial is a second-order one. We set our requirements in terms of percentage overshoot and settling time, and we retrieve the natural frequency and the damping ratio, which define our desired second-order polynomial. As you might guess, the next step is to set this mathematical equality to retrieve the PID gains. This time though, this equality is equivalent to a system of 5 equations with 6 unknowns. This means that we have to insert another equation or arbitrarily set the value of one unknown variable. Here we have chosen to set c equal to 300. And at this point we can solve the system of equations, retrieving the missing coefficients of the residual polynomial and the PID gains and time constants. All the numerical computation have been performed in Compose. So let's open the Compose script, which also draws the root locus and computes the step response of the linear model of the BBT. Let's run it. We can see that in fact we get the same values that we have reported in the slides. If we look at the root locus, we see that there are 4 poles and 2 zeros. All the 4 poles lie on the left half plane, which means that they have negative real part, hence the system is stable, and the 2 poles which lie on the real axis are the poles of the residual polynomial. Their negative real parts are bigger in absolute value compared to the other 2 poles, hence as first approximation we can neglect their dynamics. Also, the 2 zeros are on the left half plane, which makes the system faster, but since we have not taken them into account during the design phase, we have neglected their contribution to the step response. Hence, the overshoot we get is bigger than what we have designed. The percentage overshoot is roughly 25%, while in our design it was set to 5%. This means that the mathematical method we have used, even though it's extremely elegant and simple, is not suitable for properly designing the PID controller. But for example, it can be used to find the initial value for an optimizer, which eventually will produce the right controller values, as we will do in another video. Now let's see what happens when we increase C value to 8000. Let's have a look at the step response. The system seems to be way faster than before, and let's try to understand why. If we look at the root locus plot, we can see that the zeros are so close to the dominant poles. Hence, the dominant pole's dynamics is almost cancelled out by the zeros. As a result, the dynamics of the system is mainly determined by the poles of the residual polynomial, which are far on the left. Now let's deploy our controller on the real BBT. In this model, we can see that we have implemented a PID controller leveraging the PID block, and the controller gains are defined in the initialization tab. As input, we are giving a step reference in the Y direction. Let's run it. We can see that the overshooting is pretty big. If we consider the linear model, the overshooting is roughly 32%, that is bigger to the 25% we have found before during the design phase. And this is due to saturation, and we will discuss it in a few minutes. But before, let's verify that the integrator is able to eliminate steady-state error. So let's rerun it. This time we introduce some external disturbance, for example lifting the BBT on one side, and we can see that the PID control, thanks to the integrator term, is able to eliminate the steady-state error and bring back the system to the reference. We could have been able to prove it also looking at the linear model, and let's quickly do it here. This is the block diagram, which also includes the external disturbance. The position of the ball is determined by the reference and by the disturbance, as written in this algebraic equation. In the Activate simulation, we set the reference to a step. Here, for sake of simplicity, we set it to a unitary step, which in the Laplace variable s is expressed as 1 over s. Also, we can approximate the external disturbance we've inserted as a step. And for the same reason as before, let's use a unitary step. At this point, we can leverage the final value theorem to see what happens in time domain. With some basic mathematical analysis, we can see that the disturbance is rejected, and as a result, there is no steady-state error, as at the beginning of the video we have anticipated through that table. And now let's switch to saturation. So far, we have seen that the saturation affects the system performances. Generally, it makes the system slower. In case we are also using the integral action of the PID controller, we have to consider carefully the saturation, and let's try to understand why. Let's identify the saturation as a saturation block. Given a certain input signal, the output signal results to be a bounded version of the input one. Practically, saturation might occur due to hardware limits or external constraints or safety conditions. For example, if we have a certain motor, we can't ask that motor to produce a torque which exceeds its maximum torque. Since saturation is limiting the controller command, it follows that a system with saturations is lower compared to a system without saturations. In our case, the rotation of the motors is bounded from -45 to +45 degrees. Now, let's understand why we need to consider carefully the saturation when we have an integral action in our controller. And to do that, let's introduce integral wind-up. In PID control, integral wind-up is that situation where a large change in set point occurs and the integral term accumulates a significant error during the rise, and this causes an excessive overshooting. When saturation occurs, the system is lower, hence the rise takes a longer time. It results that the wind-up effect is magnified because the integrator accumulates a bigger error. From the cross point on, the error gets negative, hence the controller should change direction. But before, the integrator has to be discharged. This causes the controller to be non-responsive and, in the worst scenario, might also generate instability. Hence, we should find a way to prevent it. And we do that through the implementation of the so-called Antiwind app. Antiwind app is a term used to identify those techniques which reduce or prevent the effect of saturation on the wind up. Hence, it makes the controller more responsive. There are more implementation schemes which can be used. Here we will use the back calculation one. And for the implementation, it's convenient to split the PID into its 3 actions, as we've done here. Now we can add the Antiwind app scheme that will only affect the integral action. We can see that when the controller command does not saturate, the controller behaves exactly as without the Antiwind app. On the other case, when the controller saturates, the Antiwind app scheme prevents the integrator from charging too much. And let's see how the integrator term is affected by the Antiwind app through this Activate model. In this Activate model, we are using the linear model of the plant and we are comparing 3 different versions of the controller. The first one is without saturation, the second one is with saturation, and the third one is with saturation and with Antiwind app. And as input, we are giving a step reference in the Y direction. Let's run it. Of course, we see that the system without saturation is faster than the other 2, but we can also appreciate the fact of the Antiwind app in reducing the overshoot. Let's also have a look at the integral action of the controller. Now we should understand why the overshoot is reduced with Antiwind app. Comparing the red curve and the green one, the Antiwind app is preventing the integrator from charging too much. Now let's deploy the PID controller with Antiwind app on the real BBT. In this model, we find both the PID controllers with and without the Antiwind app. And thanks to the include diagram, we can easily switch from one to the other, just changing the value of this variable, which is defined in the initialization tab. Let's have a look at the PID control with Antiwind app scheme. Here we can see the back calculation scheme we have seen in the slides and the integrator action. And we have used the PID block to implement the proportional and the derivative action. We will run this model 2 times. The first time using the PID controller without Antiwind app, and let's run it. And the second time using the PID controller with Antiwind app. Let's run it. We can see that with the Antiwind app the overshoot is reduced, and this can be appreciated even more when we compare it with the case without Antiwind app, which is the blue curve here. Of course, also in this case you can try to introduce external disturbance and see that the steady state error gets eliminated. Moreover, since saturation is described by nonlinear equations, we cannot use our usual linear method to design the PID controller with Antiwind app. Hence, in the next video we will use an accurate built-in optimizer to obtain the optimal gains for the controller. That's it for this video. If you would like to deepen your knowledge regarding system dynamics and controls, we encourage you to visit the first link. In the ebook, you will find some of the topics we have covered today and many others. Moreover, feel free to share any questions you might have about Compose and Activate in the model-based development forum. Thank you for watching and see you in the next video.